All right, welcome back. Already we've done in the last lecture a case of making inferences about mu1 minus mu2, the difference between two population means. And we did two examples. The first example was midterm performance. And in one group we had males, and in the other group we had females. We were testing the difference between those two groups. And then we were looking at hours per week partying, as reported by Maclean's magazine, and we looked at St. of X versus Acadia. Now, there's something about the way these two groups are chosen, such that there's some sense of independence between them. You sample, for instance, all the males, which is independent of all the sampling of the females, and down here you sample St. of X independently of sampling Acadia. And I just want you to keep that in mind as we move on to the next topic. Okay, so I'm going to move on, and we're going to look at a new data set with two different sets of measurements. But there's going to be something different about this, and this will be revealed as we move on. So, if anyone's ever been on a dating profile or dating service like Tinder or the like, you might know about a tendency for particularly males to over-report their height relative to their actual height. So it's, I guess because it's a good thing to be tall, there's a tendency for males to over-report their height by a little bit. So there was a little study done, and all they did was they got, I think it was 15 males, got them, and they said, tell us what your height is, and they report that, and then they go and measure them, and they get the actual height, and this is all in centimeters. And I'll show you the data that comes out of this. This is not like... Right up the next slide here. So in the first column we have the reported height of the 15 respondents, and then we have the measured height of the 15 male respondents. And you can see in the first one, for instance, the reported height was 167 and the measured height was 166, so a slight over-reporting. That male was over-reporting their height by 1.64 centimeters. And then it goes down through all these individuals. So we have two sets of data here, and I'm just going to go and from that compute the mean and standard deviation of each one of the groups. X1 bar, S1, okay, it's 177, and then the X2 bar is 176.8. You get two standard deviations that you can compute from this as well, and then the N1 and the N2 are both 15. Now, note this is a small sample, but we can reasonably assume that the underlying distribution of heights and of reported heights are both approximately normally distributed, so we can relax our large sample assumption, and we can proceed on with N1 and N2 being 15. Okay. So what I'm going to do is make a little hypothesis test. I'm going to kind of briefly go through the steps of the hypothesis test to test the idea that males over-report their height. So they're reporting that they're taller than they actually are, than their measured height. Okay. Now again, before we were looking at males and females, we were looking at St. of X and Acadia, comparing those two groups. But in this case, for each of the measurements, there is they're associated with an individual or a particular experimental unit. So in this case, it's an individual male with a reported height and a measured height, and then a second individual male with a reported height and a measured height, and so on. And so for each one of these measurements, they are connected together. That is, there is a dependence of one data set on the other data set. There's a dependence on the individuals that you're measuring. Another very clear-cut example of this dependence would be if you did a weight loss study and there's before and after weights. Well, each one of those before and after weights is associated with an individual, with one of the experimental units. And so it really isn't the entire group of reported heights and entire group of measured heights that we want to look at. It is actually the difference for each individual. What's the difference between the reported and actual heights? And that's important to distinguish because it's going to have different, the difference is going to have different properties than looking at these two as different populations. So, what do we do in this case? Okay, well, we're going to go see this data again. All right, so let's do this. hypothesis test. We're going to test at alpha equals 0.1, so a little bit of a loose test, 10% chance of error. So test that males overreport actual height. All right, now we have mu1 and mu2. Okay, so the 1 class is the reported height, and the 2 class is the actual height. At the null, we assume that they're the same, and at the alternative, we assume that mu1 is going to be larger than mu2, or mu1 minus mu2 is greater than 0. Okay, again, we have alpha equals 0.1 for this test. And we ask now, is it large? No, but assume underlying distributions are normal. And so we're going to proceed on. Okay, so this is the step 1. Step 2, test statistic T, just like last lecture. The difference in the sample means divided by minus 0, the null hypothesized difference, over the standard deviation, root S1 squared over N1 plus S2 squared over N2. And if you plug all the numbers in there, you end up getting 0.6 minus 0, and the standard deviation works out to 2.91, and you get 0.206 as your test statistic. We jump right into the rejection region, and I know I'm going very quick here, but there's a reason. Rejection region, it's one-tailed, upper-tailed. All right, so what we're looking at is this t-distribution here. The upper tail contains 10% of the data. The degrees of freedom is the minimum of N1 minus 1 and N2 minus 1. But N1 and N2 are both 15, so it doesn't matter which one you pick, you get 14. So this little value here is T, 0.1, with 14 degrees of freedom. All right, we're going to go over to the T table now, and we're going to check out the critical value that defines the rejection region there. 1.345. All right, now let's take red maybe. 0.206 is obviously below 1.345, not in the rejection region. So for the final step, since t equals 0.206 is less than 1.345, not in rejection region, and so I do not reject the null. Doesn't mean the null is true, I just don't reject it. I do not accept alternative. I'd say there's insufficient evidence to claim that males overreport their height, something like that. All right, now let's think about this entire test I just ran because it's entirely wrong. All right, and the reason why it's wrong is, let's go back to the data for a second. I am going to take this entire thing, this test, and say it is the wrong approach. Okay, the approach assumes that the two samples that are taken are independent, but in fact they are dependent on the individual that's being measured. So this is actually a setup for what we call a paired difference experiment. And so I'm going to go back to this data. So over here, and you can see I've got a third column on this data now. So I've got the reported heights, I've got the measured heights, and then I've computed the difference between them. So in the first one, it's 167.64 minus 166, you get 1.64, and I've done that for each of the 15 measurements. it is on the column of the difference of these two that I perform my statistics. And the important thing is that variability that might exist in the data throughout here and variability that might exist in the data here to make a rather large standard deviation is reduced by only looking at the difference. Okay? Much like if you had weight loss data and everyone was losing, say, 3 to 5 pounds, but people could be anywhere from 100 to 300 pounds, let's say, your variability in the original data is large, but your variability in the difference is small. And that makes it, like for instance here, the 1.53, the standard deviation is much smaller. And that can make it easier to make a positive hypothesis test result. Okay, so paired difference experiment. We've got the data here, which is the data of the differences. This refers on your formula sheet to the third last box on the sheet. It's called test statistic for a paired difference. Now, effectively, everything now is the same as doing a test for a one sample mean, because it really is now just one sample. But we just use notation to talk about, instead of just using x bar, we'd say x bar diff, or standard deviation x diff, things like that. Just to remind ourselves that we're doing this paired difference experiment. At the end of the day, we get x bar, I'll call it x bar diff, right here. It's 0.59, and then I have this standard deviation of the diff. So S diff, 1.53. Those two are the values I'm going to use to perform this hypothesis test. All right, so a few notes and carry on with our computation. So the samples are dependent on each individual being measured. They kind of pair up. Before after measurements are typical too if you apply some sort of intervention on people or things. The approach we take here is you calculate the difference for each observation pair and we use these formulas. The test statistic formula is T as x bar diff minus 0, in that the null hypothesized difference is always going to be 0 for us, divided by the standard deviation, which is this S diff over the root of n. So if I remove those diff subscripts, this is just the case for a one sample mean. All right, degrees of freedom is n minus 1 as usual. It's called a paired difference experiment. And we are inferring about the parameter which I call mu diff. It's the population mean of the differences in the measurements. All right, so we got it all. We're going to try it now. We're going to do a test of hypothesis. Test that males overreport height, except now we're going to use the correct approach, a paired difference hypothesis test. And we're still going to use alpha equals 0.1. So here we go. Let's do it correct. 1. Set up your null and alternative hypotheses about mu diff, about the population difference. We assume it's 0 at the null, that things are the same, and mu diff If males over-report, then that difference should be positive between what they report and what they measure. So that's going to be greater than 0. And so I look at this thing and I note that it's a one-tailed test. It's going to be upper-tailed as well. Okay, so I'm looking for that area in the upper end of the distribution. Our alpha, just to keep it together, is 0.10, and we did this before. Is it large? No, because n diff now is 15, but we're going to assume underlying distribution is normal. And the central limit theorem will then apply, and so everything will work, let's say. Okay, so step number 2, test statistic. It's a T statistic here, so T is equal to x bar diff minus the null hypothesized difference of 0 over the standard deviation over the root of n. That's the sample standard deviation on the bottom there. Okay, to plug and chug. Let's just, from that previous slide, I'll just restate all these values here. X bar diff was equal to 0.595 or so centimeters. The S diff was equal to 1.53 centimeters. And N diff, if you want to call it that, is 15. All right, so you could put a little diff down here. I don't know if it's in the notation that way or not. Let's check. No, it just appears as n. So let's be consistent with that. Let's take off that diff and that diff there. All right, so n is 15. All right, plug it all in. 0.595 divided by 1.53 divided by the root of 15. And when you work that out, you get 1.5062 or so as my test statistic. Okay, next up, rejection region. This test is an upper-tailed test. So there's my t distribution. I'm leaving, I think it's alpha is 0.1, so there's 0.1 of the area in the upper tail. Degrees of freedom is n minus 1, which is 15 minus 1, and that's 14. And so I want here this value from the table, t 0.1 with 14 degrees of freedom. So let's walk over to the table. We've got our 0.1 and right here. So the rejection region is the same, but the test statistic up here is most certainly different. It's 0.2 before, and now it's 1.5. And in fact, that, as you're going to find out, is going to change the conclusion entirely. All right, so just a quick look here. The 1.5062 is right about here because the critical threshold value is 1.345. So that means I lie in the rejection region, and so I reject the null, I accept the alternative. So I'm on to step 4 and I make my conclusion. So since t equals 1.5062 is larger than t.114, which was 1.345, the boundary of my rejection region. Since I'm larger than it, then I'm in the rejection region. That means I reject H0 and I accept HA. And I would say that there is sufficient evidence at alpha equals 0.1 level of significance to claim that males overreport their height. And so you can see using this correct statistical approach means the difference between having a conclusion that is borne out by the evidence to make the positive alternative conclusion, versus in the previous case using the wrong statistical approach and not having the evidence to make the claim. So this was an example of a paired difference experiment, and this is the final type of hypothesis test that we cover in this class. Number. Right here, 0.10. Right here, and we're going down to 14 degrees of freedom, so that's 1.345. Good to go. 14, 0.1 and 14, so that's all the same. We just did that in the previous one. Okay, so it's 1.345.